Hi, I'm Angelina Wang, and with Sayash Kapoor, we are going to present our work with Solon Barocas and Arvind Narayanan titled Against Predictive Optimization on the Legitimacy of Decision-Making Algorithms that Optimize Predictive Accuracy. I'm going to start out by discussing a few examples of algorithmic failures in the real world. In the Netherlands, a predictive system was used to detect welfare benefit fraud, but misclassifications resulted in thousands of people losing access to their welfare. A company called Epic deployed a sepsis prediction tool in healthcare, but after deployment, this tool was found to have far worse performance than the real world and was originally reported by the developers. And in Oregon, a tool that was being considered for predicting which children are most at risk of maltreatment for intervention was found to have racial biases and dropped. In our work, we ask the question of why do automated decision systems keep failing? We point out shared critiques that exist across algorithms like these and argue for their illegitimacy. There's a variety of great prior work that point out flaws in automated decision-making and artificial intelligence broadly, making similar arguments about exercising caution in deployment. However, the scope of these criticisms can often be unclear. For example, whether a set of arguments that criticize a loan-granting algorithm would also apply to a large language model. In our work, we very deliberately scope our critique to be about a tight yet widespread category of system, such that we can make very strong claims about this precise category. We call this category predictive optimization. We define predictive optimization to have three key criteria. First, it uses machine learning to learn its decision rules. Second, it predicts future outcomes. And third, it makes decisions about individuals based on these predictions. Next, I'm going to use college admissions decisions as an example to better illustrate what I mean by this definition of predictive optimization. This Venn diagram shows how these three criteria may overlap. I'm going to walk through a few different hypothetical algorithms for college admissions, and we'll be able to see where they fall. One way we could imagine formulating a college admissions algorithm is with a set of hand-coded rules. For example, admitting any student that meets some minimum GPA cutoff and participation in some number of extracurricular activities. Many public universities, such as the University of California and University of Texas systems, have some version of this in place for high school graduates in their respective states. However, this would not be considered predictive optimization because while it is automated decision-making about a person, it does not use machine learning and is not predicting the future. In prior work by Johnson and Zhang, they discuss the pros and cons of these approaches for decision-making. Another way we could formulate college admissions is by using a machine learning model that is trained on historical decisions data by admissions officers. For example, UT Austin once used a predictive algorithm as a part of its computer science graduate admissions, which was trained to predict whether an applicant was admitted by an admissions committee. However, this is still not predictive optimization, because while this automated decision-making about people now uses machine learning, it is still not predicting or forecasting the future. As a third possibility, we could consider a machine learning model that ranks high schools by their predicted college performance and admits entire high schools to college at a time. We can consider how there are many lists that rank high schools against each other, and well-off parents may use them in selecting school districts. We could imagine that one such list is decided by a machine learning model that ranks schools based on future college admittance. While such a formulation of college admissions uses machine learning and is now predicting the future, it is not automated decision-making about people since it is predicting entire high schools at a time. While still dubious, this prediction of trends in a large group is a somewhat easier task than predicting the outcomes of individuals. In our paper, we have more details about why we selected these three criteria for predictive optimization. Finally, we consider a machine learning model that is trained to predict the GPA of each applicant at the end of their first year of college based on data in their application. Now, this is an example of predictive optimization as we have defined it. There's a lot that is very appealing about predictive optimization. Whatever achieves the greatest possible accuracy in predicting a concrete outcome of interest is what the policy should be. Rules don't merely reflect the considered judgments of policymakers, which others might call into question as being subjective. Instead, now they seem to reflect objective patterns in the real world, which stand on their own. However, in reality, predictive optimization often falls well short of this ideal. We present 7 critiques inherent to applications of predictive optimization, and Sayash will discuss this in our argument next.
Our argument proceeds in 3 steps. First, we show that predictive optimization is a distinct type of automated decision-making system and that it has proliferated widely. In particular, we went through around 387 articles, Kaggle contests, and news reports, and found around 50 real-world applications of predictive optimization. Of these 50, we chose 8 consequential applications for an in-depth case study. Simultaneously, we found 7 recurring shortcomings of predictive optimization that apply broadly, which we then evaluate against these 8 applications. We found that each of these 8 applications uniformly suffered from the 7 shortcomings. And to shift the burden of proof that an application doesn't suffer from these flaws, we also provide a rubric that can be used by developers as well as by advocates who seek to challenge these systems. So here's the 8 applications that we chose. In the interest of time, we'll take a closer look at Allegheny Family Screening Tool. So the Allegheny Family Screening Tool, as many of you may know, predicts which children are at risk of maltreatment, and based on these predictions, decides if a household should be investigated for child maltreatment. It has been the subject of several studies, including the book Automating Inequality by Professor Virginia Eubanks. Here, we'll go over 3 of the 7 flaws in the interest of time. Our paper dives deeper into all 7. So the first flaw is target construct mismatch. That is, it's hard to measure what we truly care about. Now, AFST claims to predict child maltreatment, but the construct, that is maltreatment, can't really be measured directly. Instead, the model's developers use 2 proxies for maltreatment. One is community re-referral, that is, if 2 calls are made on behalf of a child within the next 2 years. And the other is child placement into foster care. Now, you can imagine why these proxies don't really map on very neatly to the construct of interest. For instance, rather than maltreatment, community re-referral could also occur just if you have like a disgruntled neighbor who keeps calling you in. The second shortcoming is distribution shifts. So the training data rarely matches the deployment setting. And this appears particularly starkly in the case of the Allegheny Family Screening Tool, because the model relies on data only from people who use public services. It does not have any access to people's data when they use private insurance instead. So as you can imagine, this leads to people who rely on, say, Medicare to be penalized much more compared to those who rely on private insurance. A third flaw is Goodhart's law. Predictive optimization does not account for strategic behavior. We've seen one example of this already, when nuisance calls by disgruntled neighbors or adversarial associates can impact the family negatively. A second example is families who are marked as high risk. Instead of seeking out support, AFST encourages them to receive from community networks so that they're not reported again. Now, these were just 3 of the 7 critiques that we found, and we dive into all 7 of them more deeply in our paper. But our main empirical findings are that all 7 of these critiques apply uniformly against each of the 8 applications that we evaluated them on. In some cases, we have concrete evidence that one of these flaws applies to an application, which we denote with a full circle. In others, we have partial evidence, mostly due to the lack of transparency on account of the developers. We denote this by half-fill circles in the table. Now note that any one of these shortcomings on its own could be enough to challenge the legitimacy of an application. But collectively, these flaws begin to show that we need to treat predictive optimization applications with a lot of caution. And finally, our main aim here is to shift the burden of proof onto the developers. Instead of activists, advocates, researchers, and civil society members showing that an application is illegitimate after it has been released, we seek to shift this burden onto developers before releasing the applications. And to aid this, we create a rubric for assessing the legitimacy of predictive optimization, which consists of about 30 questions based on our analysis of the shortcomings of predictive optimization. In our paper, we also analyze alternatives to predictive optimization, which we couldn't really get to because of time restrictions here. But in case any of this sounds interesting, I do hope you'll give our paper a read on the website on this slide. Thank you so much.